combining like terms. Before we can start combining like terms, we need to understand what they are and what they aren't. Let's look at some different examples of what like terms are. For example, 2x and 3x are like terms. 5x squared and negative 6x squared are also like terms. 10xy and a half xy are like terms. Negative 57a squared b and 2a squared b are like terms. So looking at these, what do you see that they have in common? All like terms have matching variables, x and x squared and x squared, xy, xy, a squared b, a squared b. So in order to be like terms, they must have the exact same variable factor. Let's look at some unlike terms then. So what makes terms not alike? That would be if their variable factor is not the exact same. So for example, 2x squared and 2x. They're not like terms since their variable factor, x squared and x, are not the exact same. Negative 3y and negative 3x. Even though their coefficients are matching, negative 3 and negative 3, since their variable factors are not the same, they're not like terms. So hopefully that covers it for you, the difference between like terms and unlike terms. And now we can look at an example. The example says to simplify 6x minus 2x squared minus 9x plus 3 minus 4x squared. And the way we're going to simplify this is by combining the like terms. We start with the highest exponent, so we can put it in the standard form of a polynomial. And the highest exponent is the x squared, or the squared. So I'm going to take those two terms and add them together. We have a negative 2x squared and a negative 4x squared. Negative because of this minus sign in front of the term. And then we just combine those together. So negative 2x squared and a negative 4x squared would be negative 6x squared. Next, we go to our x terms, our linear terms, because they have an exponent of 1. This is a positive 6x, since there isn't a minus sign in front of it. Then we have a minus 9x. So 6x minus 9x would be negative 3x, or just minus 3x. Finally, we just have this little constant all by itself. We have nothing to add to it. There aren't any like terms to add to this positive 3. So we just write down that plus 3 in the back. The constant always goes in the back. So there you have combining like terms. Pythagorean theorem. The Pythagorean theorem states that the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse of a right triangle. The legs of a right triangle are the two sides that form the right angle. The hypotenuse is the side that's across from the right angle. Let's look at two examples. Find the missing sides of the right triangles. On this first example, we're given the lengths of the two legs of the right triangle, and what we need to find is our hypotenuse. The hypotenuse, again, is the c in the Pythagorean theorem. So what we're trying to find is c. And we'll start by writing the Pythagorean theorem. A squared plus b squared is equal to c squared. A can be either one of the legs, and b can also be either one of the legs. So 4 squared plus 3 squared is equal to, and the hypotenuse is what we don't know, so we'll leave it as c, our variable that we're trying to find. Then we simplify. 4 squared is 16 plus 3 squared is 9 is equal to c squared. Then we need to combine like terms. 16 plus 9 is 25. 25 is equal to c squared. We're almost there, but we haven't found c yet. Right now we know what c squared equals, and that's 25. But to find c, we need to do the opposite of squaring, which is square rooting. So we square root both of our sides. The square root of 25 is 5, and the square root of c squared is c, which means that our hypotenuse is 5. On this next triangle, we know the hypotenuse this time. Across from the right angle is our hypotenuse, and that's given to us as 17. So what we're trying to find now is one of our legs. And this leg can either be your A or your B. So I'm going to call it my B. Again, we'll start with Pythagorean theorem. A squared plus B squared is equal to C squared. A and B are your legs, and C is your hypotenuse. So we know one of our legs, 15, so I'll substitute that for A squared, plus, we're trying to find our other leg, B squared, we don't know it, equals, and then our hypotenuse, which is our C, is 17, so 17 squared. Now we need to simplify. 15 squared is 225, plus B squared is equal to 17 squared is 289. Since we're trying to solve for B, that means we need to get B alone. And to do that, we're going to have to subtract 225 from both sides. 225 minus 225 is 0. So on the left side, we're left with B squared is equal to, and then 289 minus 225, 9 minus 5 is 4, 8 minus 2 is 6, and 2 minus 2 is 0. So again, we found B squared, but we haven't found B yet. So to solve for B, we need to take the square root of both sides. The square root of B squared is B, and the square root of 64 is 8. So that means that our other leg on our right triangle is 8. Absolute value. Absolute value is the distance of a number from 0 and is always positive. It's denoted by a pair of vertical lines surrounding the value, such as the absolute value of 3. You can think of absolute value like you're being asked a question. And the question is, how far is 3 from 0? 3 is 1, 2, 3 places from 0. So the absolute value of 3 is 3. The absolute value of a negative number and its positive counterpart are the same. So the absolute value of negative 3 is also 3 because negative 3 is also 3 places from 0. 1, 2, 3 places from 0. The absolute value of a difference, when you're doing that, the order doesn't matter. Let's look at the absolute value of a couple of differences. The absolute value of 8 minus 3 and the absolute value of 3 minus 8. When you're doing the absolute value of a difference, again, the order doesn't matter. The result will still be the same. Let's see how that happens. Start on the inside finding your difference. 8 minus 3 is 5. So we have the absolute value of 5. And again, absolute value is the distance from 0. 5 is 5 places from 0. Now we'll look at the difference switched around. 3 minus 8. 3 minus 8, you could add the inverse of 3 plus a negative 8. 3 plus a negative 8 is negative 5, so we have the absolute value of negative 5. And like we talked about over here, the absolute value of a number and its negative counterpart are the same. So the absolute value of 5 and negative 5 is the same because, again, absolute value is the distance from 0, and distance can never be negative. So the absolute value of negative 5 is also 5, since negative 5 is 5 places from 0. Graphing solutions to linear inequalities. First, we're going to graph y is greater than 1/3 x plus 2. To graph a linear inequality, we're going to graph the line as if this were an equal sign, and then if it's greater than or less than, it's a dashed line. If it's greater than or equal to, less than or equal to, we use a solid line. So since this is just greater than, we need to use a dashed line. This is in slope-intercept form. Y equals mx plus b. So our slope is 1/3. And our y-intercept is 2. So we're going to start with our y-intercept at 2, and then use our slope to find our next point. Rise 1, run 1, 2, 3. And then we'll draw our dashed line. Connecting our 2 points. The final thing we need to do to graph an inequality is to shade. But where do we shade? One way to figure this out is to pick a point on either side of the line and see if it satisfies your inequality. If it does, then that's the side you shade. If it doesn't, then you shade the opposite side. A good point to use is 0, 0 because it's pretty easy to solve for. So y is 0. Is 0 greater than, and then again we'd plug in 0 for x, 1/3 times 0 is 0, 0 plus 2 is 2. So is 0 greater than 2? No, it isn't. Which means since 0, 0 does not work, it is not a solution, then this is not the side we shade. So we shade the other side. And really everything above this would be shaded, but I'm not going to color the whole board. So this would be your solution to this inequality. Every point in this shaded region would make this inequality true. However, points on the line would not make the inequality true, since its y is greater than, not greater than, or equal to. And that's why this line is dashed, to symbolize that the points that are on this line, the points that lie on this line, do not satisfy this inequality. Now we're going to graph a system of inequalities. The same rules apply, but where you shade is a little bit different. So first we're going to graph y is greater than or equal to 2x plus 3. Since it's greater than or equal to, we use a solid line. And again, it's in slope-intercept form. So our slope here is 2, or 2 over 1, and our y-intercept is 3. So we start with 3, up 1, 2, 3. And then we use our slope, rise 2, run 1. Now we can draw our solid line through these points because, again, it's a greater than or equal to. And there are a couple of different ways you can do the shading. One thing you could do is start by figuring out where you would shade for this line. So like again, you could use that point 0, 0. 2 times 0 is 0, 0 plus 3 is 3. Is 0 greater than or equal to 3? No, it isn't. So for this line, we'd be shading on this side of the line. And we can put it like a little dot here just to remind ourselves. This is the side we'd be shading for this line. And then you can graph your other line and see where you'd shade for that one. Where they overlap is going to be the solution. And that's one way, and I'll show you another way when we're done graphing the other line. So this next line is y is less than negative 1/2 x minus 2. Less than, since it's not less than or equal to, that means we're going to be using a dashed line again. And again, it's in slope-intercept form, so our slope is negative 1/2 and our y-intercept is negative 2. So start with the y-intercept, negative 2, and then use your slope to find your next point. Rise 1, or actually we're going down 1 since it's a negative 1, and then over 2. And again, this is a dashed line because it's just less than, not less than or equal to. We're going to connect our points with our dashed line. And put our arrows on the end to signify that that line goes on. So now that we have our two lines crossing, we've actually created 4 regions. We have this region, this one, and this one. For our first line, this region was what was shaded. So now we need to see where we're shading for our next line. Is it above the line or below this dashed line? Again, I'm just going to use 0, 0 in order to check. So negative 1/2 times 0 is 0. 0 minus 2 is negative 2. So is 0 less than negative 2? It is not. So this is not where we're shading for this one. We're shading down here in this region. And so where the two shaded areas overlap would be right over here. This is your solution, since for this line we were shading on this side, and for this line we were shading on this side. So the two shaded areas that overlap is just this region right here. And another way you could figure this out is just to pick a point in all 4 of the regions. And if the point satisfies both equations, then that's where you shade. And if your point doesn't satisfy both equations, then we don't shade in that region. Graphs of functions. The first graph is a linear function. It graphs a line. The second graph is what's called a quadratic function. Quadratic functions graph a U or a parabola. The third graph is an exponential function. Exponential functions start out increasing very slowly and then start increasing more and more rapidly. This next graph is the graph of a logarithmic function. A logarithmic function is the inverse of an exponential function. We should also talk about the asymptotes of an exponential and a logarithmic function. An exponential function has a horizontal asymptote of y equals 0. While a logarithmic function, since it's the inverse of an exponential function, has a vertical asymptote of x equals 0. And an asymptote is just a line that the graph is approaching but doesn't cross. The next graph is what's called an absolute value function. And it graphs a V. It looks like a V. So they're straight lines, and then the left side is just the reflection of the right side. This next graph is the graph of a square root function. And a square root function is a parabola turned on its side, and it's just the top half of the parabola turned on its side. And then the last function is the graph, this is the graph of a rational function. And rational functions have two branches, one in the first quadrant and one in the third quadrant. If you look at this branch here, as we move from left to right, it's decreasing. And the same with the other branch, as we move from left to right, it decreases. And so there are some of the basic functions and their graphs. Linear equations. Marielle has 10 coins in her pocket. All of them are quarters and dimes, and their total value is $1.60. How many of each type of coin does she have? We can solve this by using a system of equations. We're told that she has 10 coins in her pocket and that they're all quarters and dimes. So if we use D for the number of dimes and Q for the number of quarters, then one of our equations could be her number of dimes plus her number of quarters is 10 total coins. Next, we're told that the total value is $1.60. Well, dimes are worth 10 cents. So 10 times however many dimes she has, plus quarters are worth 25 cents, so 25 times however many quarters she has will give us a total of 160. We've eliminated the decimals, so we just move the decimal over 2 times to the right for all of our numbers. So instead of 10 cents, we have 10. Instead of 25 cents, we have 25. And instead of $1.60, we have 160. But you could leave the decimals in there if you wanted to. Now to solve this system, we've got 3 options. We could graph both of these and see where they intersect. We could use substitution or elimination. And it's your choice. For this particular problem, I'm going to use substitution. So I'm going to solve for D in my first equation so I can substitute it in my second equation. So D is equal to, and I have to subtract Q from both sides, so negative Q plus 10. To solve for D, subtract Q from both sides, and you get negative Q plus 10. So in my second equation, I'm going to use negative Q plus 10 to substitute for D. So we have 10 times the quantity instead of D, negative Q plus 10, plus 25Q is equal to 160. Now we can solve for Q. To do that, first we need to distribute. 10 times negative Q is negative 10Q. 10 times 10 is 100, so plus 100, plus 25Q equals 160. Now to solve for Q, we need to combine like terms. Negative 10Q plus 25Q is 15Q. Plus 100 is equal to 160. Subtract 100 from both sides, and we get that 15Q is equal to 60. Now we divide both sides by 15, 15 divided by 15 is 1, and 1 times q is just q. We get that q is 4, which means she has 4 quarters. So how many dimes does she have? Well, we know that her number of dimes is equal to negative q, so negative 4, plus 10. So her number of dimes is negative 4 plus 10, 6. So we can say Marielle has 4 quarters and 6 dimes in her pocket. Multiplying decimals. When multiplying decimals, instead of lining up the decimal point, we line up the last digits on the right. So if we were multiplying 4 and 23/100ths times 9 and 75,000ths, we'd want to line up our last digits. So 3 is the last digit in 4 and 23/100ths, and 5 is the last digit in 9 and 75,000ths. There's my 7, my 0, my decimal, and 9. Now we multiply just like we multiply whole numbers. So starting with 5, 5 times 3 is 15, carry the 1. 5 times 2 is 10, plus 1 is 11, carry the 1. 5 times 4 is 20, plus 1 is 21. And then I'll get rid of these. For our next number, now that we're multiplying times the 7, we need a 0 placeholder. 7 times 3 is 21. Write your 1, carry your 2. 7 times 2 is 14, plus 2 is 16. Write your 6, carry your 1. 7 times 4 is 28, plus 1 is 29. Get rid of those. Then we need 2 zeros for placeholders. And when we multiply times 0, 0 times 3 is 0, 0 times 2 is 0, and 0 times 4 is 0. We just get a line of zeros. So moving on to our last digit, now we need 3 0 placeholders before we multiply times 9. 9 times 3 is 27. Write the 7, carry the 2. 9 times 2 is 18, plus 2 is 20. Write the 0, carry the 2. 9 times 4 is 36, plus 2 is 38. Then just like we would with any other whole numbers, we're going to add our results together. 5 plus all these zeros gives us 5. 1 plus 1 is 2. 1 plus 6 is 7. 2 plus 9 is 11. Plus 7 is 18. Write our 8. Carry our 1. 1 plus 2 is 3. And then we have 8 and our 3. To determine where the decimal point goes when you've multiplied your decimals together, we're going to take how many numbers there were behind our decimal in our first number and how many numbers there were behind our decimal in our second number and add those together. So since we had 2 numbers behind the decimal here and 3 numbers behind the decimal here, then our result will have 5 numbers behind the decimal. 2 plus 3 is 5. 1, 2, 3, 4, 5. So this is the result of multiplying my 2 decimals together. Multiplying radicals. You can multiply and divide radicals even if they aren't alike. To multiply radicals, first multiply the coefficients and then do the same with the radicands. Finally, simplify if possible. Let's look at 2 examples. First, we have 3 square roots of 5 times 2 square roots of 11. We're going to start by multiplying our coefficients. 3 times 2, and then we multiply our radicands. So that's the square root of 5 times 11. 3 times 2 is 6. Square roots of 5 times 11 is 55. 55 is not a perfect square, and it also doesn't have any perfect square factors. We can see, because we've pretty much already factor treated here, 55 is 5 times 11, and neither one of those are perfect squares either. So this can't be simplified, therefore 6 square roots of 55 is our answer. Let's look at 4 square roots of 6 times the square root of 3. We're going to start by multiplying our coefficients. 4 times, and the coefficient of the square root of 3 is just 1. So 4 times 1 is 4. Then we have the square root of 6 times the square root of 3. So we have 4 square roots of 6 times 3 is 18. Now 18 is not a perfect square, but it does have a perfect square factor. So we're going to simplify it. 4 square roots of, the perfect square factor of 18 is 9. So I'm going to rewrite it as 9 times 2, which means this is 4 times the square root of 9 times the square root of 2. So we have 4 times the square root of 9, and the square root of 9 is 3. So this is really 4 times 3 times the square root of 2. So when we multiply this all together, 4 times 3 is 12 times the square root of 2, 12 square roots of 2. Percent change. Percent change is found by taking the original amount minus the new amount, finding the absolute value of that, dividing that number by the original amount, and then finally multiplying by 100. When you divide these two values, you're going to get a decimal, so to get our percent change, we have to multiply by 100. Let's look at a sample problem. If a pair of pants cost $24 last week and were marked up to $30 this week, what is the percent change? So we're going to use our percent change formula to find it. Now this percent change would be a percent increase since we went up from $24 originally to $30. If it had been reversed, say the pair of pants cost $30 last week and only $24 this week, that would be a percent decrease. But for this problem, we're doing an increase. So my percent change, or percent increase in this case, is the absolute value of the original amount minus the new amount. So the absolute value of original amount, 24, minus new amount, 30, divided by the original amount, which is 24, and then we have to multiply this times 100 to achieve our percent. So 24 minus 30 is negative 6. You can add the inverse to find that. And the absolute value of negative 6 is 6, since absolute value is distance from 0. So that's 6 out of 24 times 100. And 6 divided by 24 is 25 hundredths. So 25 hundredths times 100 would give us a percent increase of 25%. Rates and unit rates. Ratios are considered rates when they compare two different units, like miles per hour or cost per ounce. A unit rate is one in which the numerator of the fraction is compared to a denominator of 1 unit. That way you can tell, for instance, like how much just 1 ounce of something costs. And you'll see unit rates a lot at the grocery store under or next to the price of an item. It'll tell you how much that item costs for every 1 ounce or for every one thing in the package. So let's look at a problem dealing with rates and unit rates. Dave is driving 240 miles to his aunt and uncle's house. If he gets there in 4 hours, how many, and here's the key right here in the question, how many miles per hour did he drive on average? In that question, they're telling you how to set up the problem. They're telling you to put miles over hours. So we're going to start with that. Miles per hour. And now we can substitute the information in from the problem. So they told us how many miles. He's going 240 miles. And they told us how many hours. 4 hours. So we can put that into our rate, 240 miles for his 4 hours. So right now this would be considered a rate since we have 2 different units, our miles and our hours. But to determine our unit rate or to figure out his average, we would need to divide or simplify our rate to find our unit rate. So if we want to have a denominator of 1, then we're going to have to divide 4 by 4 to get our 1. And if we divide our denominator by 4, then we must also divide our numerator by 4. 240 divided by 4 is 60. So again, this is miles per hour. So what this unit rate tells us is that on average, he was going 60 miles for every 1 hour. So your answer could be written as 60 miles per hour is how fast Dave was going on average.
In math, we have rational numbers and we have irrational numbers. So we're going to be taking a look at rational numbers, which have 4 different categories, and those are integers, percents, fractions, and decimals. So we're going to define each of these. Even if you're already somewhat familiar with them, we're going to go ahead and define them and give some examples. So starting out with integers. Integer is a positive or negative whole number or 0. So 9 would be a whole number. It would be an integer because it's a positive whole number. Negative 6 is an integer because it's a negative whole number. Then, of course, 0 is an integer because we said it was. And so now we move on to percents, which is kind of a more complicated way to say percent is a part per 100. So an example of a percent is 20%, which we could also write as 20 parts per 100. But the important thing here is just you know what a percent is, like 20%. Then fractions, which is a proportion. So an example would be 20 divided by 10 or 2 divided by 4. And of course we have decimals, so this is where we have an integer, maybe 1, maybe 89, maybe 0. And then we have a decimal place, and then we have numbers after the decimal, like 20.53. So we have our integer, we have a decimal, and then we have numbers after the decimal. So integers, percents, fractions, and decimals are all rational numbers, usually. There are some rules. So in order to be a rational number, just summarize, it either has to be an integer, like we talked about. If it's a number like 9, negative 6, 0, it's always going to be a rational number. It gets more complicated when we come to fractions and decimals. If it's a fraction, it has to be an integer divided by an integer. And this integer cannot equal 0. So it's an integer divided by an integer. So 7 divided by 4 cuts it. That works. Now, decimals are a little bit more complicated because it either has to be a terminating decimal or a repeating decimal. So an example of a terminating decimal would be something like 2 divided by 4. From that you get 0.5. It ends right there at the 5. For a repeating decimal, you do 1 divided by 3 and you get 0.3333. It goes on forever. But notice we're getting the same number every time. So really you could erase all of these 3's and just put a line over the 3 showing it's a repeating decimal. What you don't want is a decimal like pi, where you have 3.1415926, 5359. It just keeps going on and on. So there's no ending to it, so it's not a terminating decimal, and there's no pattern to it, so it's not a repeating decimal. That's what an irrational number is, one that just keeps going like this. These numbers, they have basically a stopping point. And so that's what we're looking for. And so the reason I say that a fraction has to be an integer over an integer is because when you divide an integer by an integer, you get a clean number. You get a decimal that's repeating or terminating. When you start dividing a decimal or a fraction by a number or a fraction by another fraction, that's when you're going to start getting messy. So really, if you're wondering whether a fraction is a rational number, what you can do is go ahead and divide it out and then look at the decimal and decide whether it's terminating, repeating, or non-ending. And that's how you can determine if it was a rational number.
Ratios. A ratio is a comparison between two quantities. You can think of a ratio like a fraction. And since it's just like a fraction, a comparison of two numbers, it is treated a lot like a fraction, meaning you're going to simplify it anytime you can. Let's look at this problem. Suppose a sampling of fish from a local pond contains 12 bass, 8 catfish, 38 minnows, and 4 trout. What is the ratio, so the comparison of two numbers, of bass to minnows? Now, when they ask you this question, they're telling you exactly how to set your ratio up. Since it says bass to minnows, we read left to right. We also read from top to bottom. Since a ratio is a fraction, then they're telling you what your numerator should be and what your denominator should be. So our ratio is going to be bass to minnows. And now we can substitute how many bass and minnows we have. According to our problem, we have 12 bass and we have 38 minnows. So that ratio would be 12 to 38. But again, since this is a fraction, we're going to simplify it if we can. And 12 and 38 do have a GCF of 2, so we're going to divide 12 by 2 to get 6, and we'll divide 38 by 2 to get 19. Therefore, our ratio of bass to minnows is 6 to 19. But that's not the only way we can write a ratio. We could also write it as 6 to 19, or as 6 to 19. And these all mean the same thing, and they all give you the same information, that for every 6 bass in the pond, there are 19 minnows in your pond. It is important, though, the order of your numbers. Since the ratio they were asking for was bass to minnows, your bass number should be first, and then your minnows number. So make sure you put it in the right order. That is very important. Scatter plot. Any collection of data can be displayed on a scatter plot. You would plot the data points on a coordinate grid and then just not connect the points, and that's how you get a scatter plot. So here are 3 examples of 3 different scatter plots. This first scatter plot could be said to have a positive correlation. Because the data points are going generally up in a straight line. This next set of data would be said to have a negative correlation. Because these data points are decreasing. And then this last graph of data has no correlation at all. The points are completely scattered. So this would be no correlation. If there is a correlation in the data, however, and there won't always be, and it won't always be in a straight line like these are, but if there is a correlation in the data, then a line or a curve of best fit can be found. If the data is like these two, where they're going pretty much in a straight line, then you'd find a line of best fit. And the line of best fit would just be a line right down the center of the points that you could then find an equation for. And you could find the equation for this line using any 2 points that are on the line, and then plugging that into the y minus y1 equals m times the quantity x minus x1, or the point slope form of a linear equation. And then you could use that line to predict other points that are not graphed on the graph. And you could do the same thing for a negative correlation. But again, the correlation doesn't always have to be in a straight line. Sometimes it's in a curve. And that's just a little introduction to scatter plots. Simplifying radicals. Many times the radicand, or the number under the square root sign, isn't a perfect square. But you can still simplify the expression if it contains a perfect square. Let's look at 3 examples. And we're going to use this rule that the square root of AB is equal to the square root of A times the square root of B. We're going to break down our numbers. So 75 is not a perfect square, but it does contain a perfect square, because 75 is 25 times 3. So I'm going to rewrite the square root of 75 as the square root of 25 times 3. 25 is a perfect square. Now I can use this rule that the square root of A times B is equal to the square root of A times the square root of B. So I'm going to rewrite this as the square root of 25 times the square root of 3. And now that I've broken it up, I can actually take the square root of 25. So the square root of 25 is 5 times the square root of 3. So 5 square roots of 3. So the square root of 25 in simplest radical form would be 5 square roots of 3. Let's look at the square root of 18. Again, 18 is not a perfect square, but it does contain a perfect square. So I could rewrite the square root of 18 as the square root of 9 times 2. And 9 is a perfect square. So now I'm going to use my rule again, and I'm going to write it as the square root of 9 times the square root of 2, so that now I can take the square root of my perfect square. The square root of 9 is 3, and 3 times the square root of 2 is simply 3 square roots of 2. Last one, 600, or the square root of 600. So again, 600 is not a perfect square, but it does contain a perfect square. So I'll rewrite this as the square root of 100 times 6, 6 being our perfect square. And then I can use my rule again and write it as the square root of 100 times the square root of 6. And we can take the square root of 100. The square root of 100 is 10, since 10 times 10 is 100, times the square root of 6, 10 square roots of 6. Solving a quadratic inequality. Solve x squared minus 3x minus 10 is greater than 0. One way we could solve this inequality is to graph it. And then Since it's a greater than sign and not or equal to, we would graph a dashed line, and greater than means to shade above the parabola. And so the solution set would be all those coordinates in the shaded region. If this were a less than sign, then we'd simply shade below the parabola, and all the coordinates, again, in the shaded region would be the solution. The other way to solve is to factor, and that's the way we're going to do it here. So I'm going to factor x squared minus 3x minus 10. And I'm going to solve it as an equation first. So I'm going to change our greater than to an equal sign. So I know this is an x and an x, so that when I FOIL, I get my x squared. And I need two numbers that have a product of negative 10 and a sum of negative 3. So those numbers that have a product of negative 10 and a sum of negative 3 would be negative 5 and positive 2. Negative 5 times 2 is negative 10, and negative 5 plus 2 is negative 3. And now we'll use the zero product property to solve. X minus 5 equals 0. X plus 2 equals 0. Add 5 to both sides. So x equals 5. Subtract 2 from both sides. And x equals negative 2. Now our solution set is either the set of numbers that's between these two numbers, or it's the set of numbers that's outside these two numbers. So if it's between negative 2 and 5, we'll just pick a number and we'll see if it works. And an easy number to pick between negative 2 and 5 is 0. And if 0 does not satisfy our inequality, then our solution is not the set of numbers between these, but instead it's the set outside. So we're going to try 0, because that's a number between negative 2 and 5. 0 squared is 0, minus 3 times 0. 3 times 0 is 0. So 0 minus 0 minus 10, that's negative 10, is greater than 0. That's not a true statement. Negative 10 is not greater than 0. So our solution set is not the set of numbers between these numbers, but instead it's the set of numbers outside. So x is less than negative 2, or x is greater than 5. And those values, if you pick a number, say 10. 10 squared is 100. 100 minus 30 is 70. Minus 10 is 60. And 60 is greater than 0. And see, that's a number that's greater than 5, and that number works. And then if you tried another number back here, a number that's less than negative 2, say negative 5 or even negative 10, negative 10 squared is 100. Negative 3 times negative 10 is 30. So 100 and plus 30 is 130, minus 10 is 120, and 120 is also greater than 0. So you can see that the set outside these numbers, numbers that are less than negative 2 and numbers that are greater than 5, do satisfy our inequality, while the numbers between negative 2 and 5 did not, like 0. Solving problems with quadratic equations. A swimming pool is 11 feet longer than it is wide. The area of the pool is 276 square feet. What are the dimensions of the pool? Dimensions being our length and our width. So what they're asking us to find are the length and the width of the pool. They gave us some clues that we can use. First one is that the pool is 11 feet longer than it is wide. So if we said the width was x, then the length would be the width plus 11. Now to find the area of a rectangle, the area is length times width. And they told us the area. And we have expressions for our length and our width, so we're just going to substitute. The area is 276 square feet is equal to the length, which is x plus 11, times the width. So x times the quantity, x plus 11. And then we can simplify by distributing. So 276 is equal to x times x is x squared, and x times 11 is 11x. This might look a little familiar to you. If we subtract this 276 from both sides, then we get our standard quadratic equation. 0 equals x squared plus 11x minus 276. And now that we have that, we can factor it to find what x is. So 0 equals x and x, because when we FOIL, x times x gives us x squared. Now we need to find two numbers that have a product of negative 276 and a sum of 11. So that would be positive 23 and negative 12. 23 times negative 12 is negative 276, and 23 minus 12 is 11, or plus a negative 12 is 11. Now we can use the zero product property to solve for x. So x plus 23 equals 0, and x minus 12 equals 0. To solve for x here, we subtract 23 from both sides, and x equals negative 23. To solve for x here, we add 12 to both sides, and x equals 12. Now, if you'll remember, x was our width. And it doesn't make sense for our width to be negative, so this answers out. Which means our width is 12 feet. So width equals 12 feet. And if our width is 12 feet and our length is 11 feet longer than that, then 12 plus 11 is 23. So the length is 23 feet. And there are dimensions of the swimming pool. And we can check that by multiplying 23 times 12, and you will in fact get 276 square feet. So that means that we solved it correctly.
When dealing with probability, we have theoretical probability and experimental probability. So right here we have the data from 3 games of football. And so the quarterbacks completed this many passes out of this many passes attempted. But it's also said that there's probability of this quarterback completing 60 passes out of every 100 attempts. So if we're to look at the probability here, so I'll label that as P, the probability of completion, we have to take a look at the theoretical number of completions and put that over the total pass attempts. And so in this case it's 60 over 100, which translates to 64%. So this is the theoretical probability. But right here we have this data right here from 3 games. And so here, if we're to take a look at this probability, we're going to do the same thing. We're going to take the number of completions and put it over the total pass attempts. And so in this case, we have 51 completions over 67 pass attempts, which translates to 0.76, which translates to 76%. So if you notice here, these two percentages are a lot different. And that's the difference here between theoretical probability and experimental probability. Theoretical probability is calculated by just looking at the odds of what's going to happen. So somebody could examine this quarterback's throwing ability, look at his opponents, and say, okay, the theoretical probability here is that he'll complete 60% of his passes. But then when it's all said and done, we have experimental probability, which is what he actually did, which is a 76% chance. Another example of this would be, say, rolling a die, for example. So say you're looking at flipping a coin. And so the probability of landing on heads when flipping a coin is 1/2. So say you flip a coin 6 times. And so 4 times it lands on heads, and twice it lands on tails. And so really, these should be even. Really, for there to be a 50% chance of landing on heads, then you should have landed on heads 3 times, and the coin should have landed on tails 3 times. So this is, right here, the theoretical probability. Because when you flip a coin, there's a 50-50 chance of what it'll land on. There's a 50% chance it'll land on heads and a 50% chance it lands on tails. So if you were to flip a coin 6 times, the theoretical probability is that it would land on heads 3 times and tails on 3 times. But right here we have the experimental probability, and this is what actually happened. So that's the difference between theoretical and experimental probability.
Scientific notation. Scientific notation is used to write larger numbers in a shorter form. And the form is a times 10 to the n, where a is a number that is greater than or equal to 1, but it's less than 10. And n is the number of times we must move the decimal, and in which direction. Let's take this number, 230,400,000. It's a pretty big number. We can write this in scientific notation by taking our decimal, which is at the end of our number, and moving it 1, 2, 3, 4, 5, 6, 7, 8 places to the left, so that our number is now 2 and 304 thousandths. And you see my A is a number between 1 and 10. 2 and 304 thousandths is greater than or equal to 1, but less than 10, times 10 to the 8th. And this number is the same as my original number. We can also use scientific notation to take very large decimal numbers and write them in a shorter form. We do the same thing. Our A has to be greater than or equal to 1 and less than 10, which means we need to move our decimal 1, 2, 3, 4, 5 places to the right, so that it becomes 2 and 304 thousandths times 10 to the negative 5. And that negative exponent lets you know that that's a very, very small number. It's a decimal. It's less than 1. Whereas a positive exponent tells you that it's a very large number. We can use these exponents to compare our numbers very quickly and easily. Looking at these two numbers in scientific notation, I can tell that 1 and 51/100ths times 10 to the 5th is the larger number because it has the larger exponent. So it's a great method for very large and very small numbers.